Okay, reviewing for our test for tomorrow. Okay, the first thing we started off with was this worksheet where we kind of discovered the basics of parabolas, kind of did a little discovery of it. I'm not going to go through these problems again, but what we are going to do is review some of the basic vocab, important terms that we talked about. Independent and dependent variables. Okay, the x-axis is always independent, the y-axis is always dependent. If time is a part of the problem, time is always going to be the independent variable. It's always going to get the x-axis. The language that kind of goes along with that is that what happens on the y-axis depends upon what is going on with the x-axis. Domain and range, of course, domain means all of the possible x values of a problem. Range means all of the possible y values for a problem. That doesn't mean that the domain and the range are always going to follow the entire parabola, okay, because we have different situations, different problems where the domain or the range may be interrupted or blocked by what the problem's trying to do. Like the example with the ball the other day, okay, you can throw the ball up in the air, it's going to go up to its peak, it's going to come back down, the parabola is going to continue off to negative infinity, but the ball could not continue off to negative infinity because the ball was going to strike the ground at some point, and that's going to block the range from going any further. So on domain and range, okay, aside from the definition, you need to remember what the apply the problem to what the domain is or what the range is. We also discovered that our parabolas are going to have reflectional symmetry. In our parabola, we will have a line of symmetry, and whatever it's doing on one side of the parabola, it'll also do on the other side of the parabola. We ran into the words increasing and decreasing again. We don't use these much, but if you do run into them, just remember increasing simply means the graph is traveling upwards, and decreasing means it's traveling downwards. Okay. We also got a definition for functions for about the 6th time this year. Okay, and remember the basic definition means in order to be a function for any x value that you come across in your graph, there is one and only one y value that goes along with it. All the parabolas we've seen have been functions. Okay, they've been upward or downward traveling parabolas. Anywhere that you move along the x-axis, there is only one y value that you will run into at that particular location on the x-axis. The parabola is only that way. Okay, what y'all don't really realize, and I'm just going to kind of put the bug in your ear now, the parabolas that we've seen have all been vertically oriented. They're all either going upwards or they're going downwards. Okay, but there are parabolas that go sideways. Okay, some do go to the right, some do go to the left. And those, if you ever happen to run into them, are not functions, because think about a parabola that's traveling off to the right. Okay, if you find an x value somewhere out there in that parabola, when you look up from that x value, you're going to find a point on the parabola. When you look downward from there, you're going to find another point on the parabola. That means for one x, there are two different y values that go with it. That would not be a function. Okay, but we're not really going to deal with those in Algebra 1. That's more of an Algebra 2 and maybe even pre-calculus topic. But there are parabolas that go sideways that would not be a function. The parabolas we're working with are functions. This is something that the success spiral videos have been talking about today. Intercepts. Okay, y-intercepts. Y-intercepts happens when the x value of an equation is 0. Y-intercepts happen when the x is 0. Now, if you have a graph, you can obviously just look at where does it cross the y-axis, and if you can get that value out of the graph, then good for you, you've got it. If not, if you have an equation, all you have to do is set x equal to 0, solve for y. That'll tell you exactly where your y-intercept is. And the flip side of that would be x-intercepts. X-intercepts happen where your y value is 0. And if you have a graph, you can look at the graph and see where it crosses the x-axis, and that's fine. But if all you have is an equation, then you need to set your y value equal to 0, and you can solve for x. That'll tell you exactly where your graph crosses the x-axis. Now, we've probably noticed this a little bit, but we haven't really said it. Okay, our parabolas that are functions are going to have a y-intercept. Most of the time, they've had a y-intercept in the graph. We've been able to see it, or we've been able to see it in the charts. It's been very easy. Okay, but keep in mind, like I said, our parabolas have been vertical. So even if our parabola doesn't happen to hit the y-axis in our graph, well, it's going to continue on vertically forever. That means it's going to continue drifting outwards forever. It's going to get wider and wider and wider until it eventually covers the entire x-axis. Okay, so it will hit the y-axis somewhere. Our parabolas are going to have a y-intercept, whether they like it or not. What we haven't really talked about much about is x-intercepts. And the only thing you really need to know about x-intercepts in Algebra 1 is that, you know what, your graph might hit the x-axis, it might not. Okay, depending on where the parabola is in the graph, if it's been moved up or down, or which direction it's going in the graph, whether it's traveling upwards or traveling downwards, it's going to change whether or not it hits the x-axis. Okay, if you think about a parabola, an upward traveling parabola, an increasing parabola, if it's moved down in the graph, it's going to start downward, and as it travels up, it's going to have two different places that it hits the x-axis, and then it's going to continue on. So it's possible it might have two x-intercepts. Okay. On the other hand, we might have a parabola that starts on the x-axis, single point, and then it opens up and travels away, in which case it only has one x-intercept. Okay. On the same flip side of that is that the parabola could be moved upwards in the graph and then open upward. Okay, so if it's already higher than the x-axis and then travels up from there, it's not going to have any x-intercepts at all. So if you run into a question that starts talking about x-axis intercepts, you're going to have to think about the question kind of a case-by-case basis and go, okay, does it hit the x-axis, yes or no? And if it does, how many times will it hit the x-axis? It'll be a 2 or a 1 or a 0. Okay, so that was kind of that. Okay, the next day we started looking at some basic changes to the quadratic equation. We had a lot of trouble with these, okay, but follow along. Hopefully we can do a little better with them right now than we did when we first started doing this. Here's a couple of equations, okay? Now, are these quadratics? Are these parabolas? No, they're not. Why are these not parabolas? These are lines. Why are they lines? Say again? No squareds, okay? You got x to the first, y to the first. When both of the variables are first dimensional, straight line. When you change one of them's going to be first dimension, and change one of them to a second dimension, now you've bent the graph, okay? That's what's going to cause it to be parabola. So these are lines, okay? But the same things we've been learning about these equations and changes we make to the equations, going to do the exact same thing to any kind of a graph, whether it's a straight line or a parabola or a cubic equation. It's going to do this to all of it. Okay, so let's look at these questions that we have here. What is the change in the graph from y1 to y2? And we actually had the calculators, and we were typing them up, and we were looking at them, but I'm hoping we can do it without the calculators now. Look at these two equations, y1 and y2. What has changed between these two equations that are typed right there? Okay, you got a +2, but what does that +2 do to the graph? Moves it up, exactly. Okay, y1 is passing through the origin because there's nothing written right there. y2 has a +2. It's been shifted up 2 units. Plain and simple. It's that easy. Okay, what is the coordinate of the y-intercept for of y1? Well, where do we say it crosses? It crosses the origin. What's the coordinate there? 0, 0. Okay, that's easy. What's the coordinate of the y-intercept for y2? Where's this one going to cross at? It's not 2, the coordinate, okay, the full value. 0, comma 2. Okay. Predict the coordinate for the y-intercept of this equation down here at the bottom. Where would be the y-intercept for this one? Y equals x minus 3. 0, -3. There you go. It's really that simple. Okay. Now we apply the exact same thing from the lines that we were just looking at to parabolas that we're now looking at. What's the coordinate of the y-intercept for y1? Where's the y-intercept for this first one? 0, 0. What is the coordinate for the y-intercept of y2? Where's this one cross at? 0, -4. What would be the coordinate of the y-intercept for this bad guy down here at the bottom? 0, +26. It's really that easy. Okay, so then we made a summary statement. What do we know about the value c? What does it tell us about the problem? Simply, where does it cross the y-axis? Or a different language for that is there a vertical shift? Has the graph been moved up? Has it been moved down? That will be told to us by this value c. Okay, so we kind of learned about that right off the bat. Now we started changing some other things in the equation. Okay, so we typed up y1 and y2 and then asked what change is being made in the graph from y1 to y2. Well, what does change right there? Obviously, it becomes a 2, okay, but what does this mean? these first two. What does it mean when the number in front of the independent variable gets bigger? It's not a shift. It changes the speed of the graph. The normal speed, the parent function speed is 1. Okay, when you change that to a bigger number, it makes the graph be in a bigger hurry. That's what we call stretched. Okay, it's stretched. The graph is moving faster vertically than it used to. So what change is made in the graph from y1 to y2? Y2 is in a bigger hurry. Okay, it has been stretched. What change was being made in the graph from y2 to y3? What changed from these second two? Well, it's different. One's positive, one's negative, but what does this do to the graph? Turns it upside down. Exactly. That's all it does. It flips the graph upside down. It wants to go upward. If you change it to a negative, it's going to cause it to go downward. Instead of increasing, it's decreasing. Predict what would be what the following equation might do. Y equals negative 4x. Negative. What's that negative going to do? It's going to cause it to go downward instead of upward. And the 4, we've got an even bigger number in front of the variable. That's going to speed it up even faster. Okay. Got to remember, if it's a 1 or if it's bigger than 1, the graph is being stretched. It's moving faster. If it's a number smaller than 1, some fraction smaller than 1, the graph is being compressed. Okay, it's moving more slowly than it wanted to. Okay, and we did the exact same things over and over and over again. Okay, so what statements did we make about this a value? Y equals ax plus c, or ax squared plus c. What did a do? Two things. It told us, is it increasing or decreasing? Okay, is it going upward or downward? And secondly, has it been stretched? Has it been compressed? Or is it at its normal speed? Okay, all that is determined by A. Okay, so we had a few more and we kind of played around with them for a while. This equation, y equals x squared. Somebody tell me what kind of equation that is? Say again? It's a parabola. Okay, what else about it? This guy has a particular name. Say again? Parent function, exactly. Okay, it's the parent function. How do you know it's a parent function? Or how do you know any function is a parent function? Not necessarily the square part of it, because I could take the square away and it would still be a parent function. I could change that square to a cube or a fourth or a fifth, and they would still be parent functions. But why are they parent functions? Okay, we need to know this. They're going to hit us with a question, I guarantee it. They do every year. Okay, it's a parent function because nothing has been changed. There's no value in front of x or x squared or x cubed or x to the fourth or anything it is. It's positive. It's a 1, and it's not vertically shifted at all. Okay, it's just the basic function doing its normal thing at its normal position. Nothing's been changed. Okay, that's what makes it a parent function. All right, so that was that. The next thing we did was we started trying to figure out, okay, let's look at some points that are on our quadratics, and let's see if we can figure out what type of equations are going to be applied from the type of points that we're given. So we started trying to read the points and decide, does it need a vertical shift to be to fit these points? Does it need to be stretched or compressed to meet these points? Does it need to be positive or negative to meet these points? Stuff like that. Okay, so we're trying to decide, is it a y equals x squared type of formula? Is it y equals x squared plus c? Or is it y equals ax squared? Or is it y equals ax squared plus c? Okay, so looking at these points, okay, what we did is the first thing we did, the easiest thing to do is to decide, does it need a vertical shift? Well, have a look at these points that you have in this chart here. Is this a parabola that needs a vertical shift? Well, if it were the parent function, where should it cross the y-axis? Should go through the origin. Okay. Does this graph go through the origin? Yes, it does. Okay. This graph goes through the origin, so it does not need a vertical shift. So we would not be picking on an equation that did not have a vertical shift. So those two we were able to eliminate right there. Okay. The next thing we did was said, okay, we need to decide, does it need to be stretched or compressed in order to pass through these points? And the way that we decided that was by looking at the line of symmetry, okay, which is where the the vertex is, okay, where it's crossing the y-axis. And then we said, all right, as it moves one step in either direction, how much is it moving by? Well, from 0 to 2 was a step size of 2. What if we took 2 steps away from the line of symmetry? From 0 to 8 would be 8. Now, what we wanted to do is we wanted to compare this to how big of steps was it supposed to be taking. And the answer to how big of steps it was supposed to be taking comes from the parent function. Okay, y equals x squared. If we were to pick on these exact same points, -2, -1, 0, 1, 2, and plug those into the parent function would tell us how big are the steps supposed to be. Well, if you plug in -2 in there, you get a 4. If you plug in -1 in there, you get a 1. 0, you get a 0. 1, you get a 1. 2, you get a 4. Okay, so if this is the line of symmetry for the parent function, as we move one step away from the line of symmetry, it should be 1 units worth a step. Okay, as you move 2 steps away, should be 4 units worth of a step. Okay, and this is the way it works with the parent function for the quadratic. The first step ought to take us 1 unit away. The second step should be 2 squared, would be 4 units away. The third step would be 3 squared. That would be 9 units away. Okay, now what you do is you compare what you just found to what the parent function actually did. We were expecting it to be 1 step as we moved 1 unit either direction. What did we find? 2 units. We expected it to move by 1, instead it moved by 2. Okay, what about this next step? We expected it to be 4 units. What did it turn out being? 8. Okay, and when you look at this, you ought to be able to develop a pattern to it. Okay, we expected it to move by 1. Instead, it moved by 2. That was twice as much as we expected to get. Instead of moving by 4, it moved by 8. That was twice as much as we expected to get. Okay, so it's moving faster than it should, which means we are going to need a value in front of our x squared. So we cannot use this equation because it did not have an a. We can use this one. Okay, we needed, oh, y'all let me cross off the wrong answer choice a moment ago. We didn't need that one. That one had a vertical shift. This one didn't. Okay, so that's the answer choice that we really would have needed right there. Okay, it was stretched because our step sizes are not what we were expecting to get, but it did not have a vertical shift. Okay, well, look at it again. Okay, here's a set of points. Does this parabola need a vertical shift? Okay, there's its line of symmetry. Does it go through the origin? It does not. This one needs a vertical shift. So we would take anything out that does not have a vertical shift. Okay, there's that line of symmetry. It's moving as you can move one step either direction, it moves by 1. As you move 2 steps either direction, it moves by 4s. As you move 3 steps, it moves by 9. Is that what the parent function suggests that we do? 1 squared, 2 squared, 3 squared. Those are exactly the step sizes that it's supposed to have. That's exactly the step sizes that the parent function has. So does it need an a value? It does not need an a value. That would have been the equation we would have selected for this one. It needed a vertical shift, but not a stretch. Okay? And you can do this over and over again. There's your line of symmetry. Does it pass through the origin? It does not. So it needs a vertical shift. Look at the steps. As you move 1 step either direction, it actually took 3 steps. 2 steps either direction, it took 12 steps. 3 steps, it took, goodness, 27 steps. Is that what we expected? 3, 12, and 27? No, we expected 1, 4, and 9. Okay, so it is absolutely stretched. Okay, so we would pick on one that needs a stretch. Okay, and that's what we did. We were basically just using points trying to identify what format our equation would look like. Okay. After that, we came back and said, okay, now that we know what equation we're looking at, okay, or what our format of our equation ought to be, here. Okay, so now we applied actual points to the situation to see if we could figure out what was going on. We've got y equals some amount of x squares and then plus or minus some number. Okay, so we started to have a look at what the actual shift should have been if it needed one and how much it was stretched or compressed if it needed that. Okay, so here we go. You just find your line of symmetries right across there. Does it need a vertical shift? Yeah, it does. Okay, how much does it need? Okay, it dropped down to 0, -4 rather than passing through the origin. That means that our equation should be whatever the x squareds are minus 4. Okay, then we can check and see, okay, what about this stretch or this compression? Let's take a look. As we move one step either direction, it did move one step on the y-axis. As we move 2 steps either direction, it does move 4 steps. 3 steps either direction, it moved 9. Those are the step sizes that it should be moving by, so the coefficient of x squared is a 1, which is what it's supposed to be. The only other thing you need to check for is the graph increasing like it should be, or is it decreasing? Is it upside down? We'll have a look at the points. Is it increasing or decreasing? Okay, let's look. We got 0, -4. Okay, so we're a little bit down on the y-axis. From -4, it comes up to -3. From -3, it comes all the way up to 0. From 0, it goes up to 5. So is it increasing? Yeah, it is. That means that this is a positive value. Our equation should be y equals x squared minus 4. And that was the equation that we came up with. Okay, looking at it again. Okay, y equals some amount of x squareds plus or minus some number. Let's have a look. There's your line of symmetry right through there. Does it need a vertical shift? Yeah, it does. How much? Positive 2. So it should be a something x squared plus 2. Okay, now let's have a look at the step size here. As we move 1 unit either direction, actually only changed 1/4. 2 steps, changed by 1. 3 steps, changed by 2 1/4. Okay, okay, is it moving by the step size that it ought to? No, it's moving very slowly. Okay, it's not moving nearly as fast as it should be. So we are going to get a coefficient this time. The question is, how big or how small should the coefficient be? Okay, well, we expected it to move by 1 on the first step. It didn't move by 1. It only moved 1/4 of that, 1/4. So actually the multiplier there is times 1/4. It only moved 1/4 as much as it should have. On the second step, 2 squared, it should have moved 4 steps. It only moved 1. So once again, it moved 1/4 as much as it should have. Okay, and you can continue that on. Okay, the third step there should have been 3 squared, 9. It only moved 9/4. So once again, 1/4 as much as it should have. Those numbers ought to keep coming out exactly the same no matter how many steps you take, and that is your coefficient. That's your A. Okay, so it's 1/4 x squared. The only other thing to decide, is it positive x squared, or a positive 1/4, or is it a negative 1/4? Well, let's look. Is it moving upward or downward? 0, positive 2. Okay, so it's sitting there on the y-axis. It goes from 2 up to 2 1/4, 2 1/4, up to 3, 3 up to 4 1/4. It is traveling upwards even though it's not going very quickly, so it is a positive 1/4, and there's your value, your equation down there already at the bottom uncovered. Okay, 1/4 x squared plus 2. Okay, and it's really the same thing over and over and over again. Okay, and again, this one I've apparently didn't erase it from last period, but there you go. You've got your line of symmetry. Okay, it's passing through 0, -6. So we have a -6 on the y-intercept, okay, on the vertical shift. And then when you look at the step sizes, we get a 3, then we get a 12, then we get a 7, a 27. We were supposed to get 149. So we got 3. That was 3 times bigger than we expected. 12 was, again, we expected a 4. That's 3 times bigger. 27, we expected a 9. So again, it was 3 times bigger. Okay, so every single time it's times 3 times 3 times 3. That means that we have a 3, okay, for our coefficient. This time, as I've already got written down there, it's negative Okay, because this one's upside down. If you look at the points, 0, -6. It's already down on the negative y-axis. From -6, it drops down to -9. From -9, it drops down to -18, -18, all the way down to -33. This one's obviously traveling downward. That's why we have a negative there on that. Okay, so that's pretty much that, and that's really the challenge of what we're doing in this unit. The last thing we did was we looked at this review sheet that we talked about on Monday and kind of finished up talking about yesterday. I'm not going over this problem again. Okay, so the only thing I really want to do was to kind of go over this again, just in case that your calculator can help you out. So I kind of gave you a little bit of step-by-step here just to refresh your memories. Okay, if you run into a problem that's not making sense, or you just want to try to rely on the calculator to think for you, okay, whatever the case may be, okay, remember that you can plot your points and you can ask the calculator to come up with an equation for you. Okay, so if you find the need to plot points, hopefully you should be okay at this by now, but it's in the statistics menu. Okay, and in the statistics menu, the very first option there is edit. Select edit. It'll bring up all of your lists. You need to type your points. Okay, in there. Whatever you put in list 1 and list 2, that's like your X's, comma, your Y's. You put all your X's in one list, all your Y's in one list. So put all your points in there. Okay, if you want to graph it, press graph. If it doesn't graph, one of the things you need to do is check your stat plotter. Okay, check your stat plotter. One of these guys needs to be on. If it's not, then it probably will not graph. Okay, so if one of them's on, it should be graphing, so something else must be wrong. But if all three of these guys are shut off, then what you need to do is just select one of them, okay, and come in here and change it from off to on. Okay, so after you do that, you ought to be able to press graph and check out your points. Now, if you find the need to get the equation, okay, this is also capable of being done by the calculator. It's in the statistics menu as well. The second column, calculate, and option number 5 says quadratic regression. Quadratic, that's our equation we've been working with. It graphs parabolas. Regression means best fit. Okay, it may not hit all the points, but it's going to do the best it can to fit into the points that we've given. So option number 5, quadratic regression. It'll go back to the home screen and say quadratic regression, but then it's going to wait for you to tell it where your data is. Okay, well, wherever you put your data in the edit column, okay, wherever you put it, select the list number. So list 1, comma, list 2. You're telling the calculator, hey, X, comma, Y, list 1, comma, list 2. Okay, from there, when you press enter, it'll tell you quadratic regression. It'll give you the generic form of the equation, y equals ax squared plus bx plus c, and it'll give you values for a and b and c. Okay, hopefully you'll be able to answer a question from that. But if you need to see the equation graphed, go into your equation editor. Okay, you'll have to write this information down on a, b, and c. Okay, but just type it up. Okay, type it up in your equation editor. You can't see everything on my little screen there because it didn't wrap around like some of the other calculators do. Okay, but type up your equation and hit graph. On the standard graph, the points along with the equation that I typed in would look like this. Very skinny, very difficult to see what's going on in that. And remember, you can get the calculator to select a better window for you if you go into the zoom, and we're operating in the statistics menu. Okay, so zoom stat for zoom statistics, and the calculator will take a better picture of the points that you have entered, and it'll of course graph the line that you typed passing through there as well, and hopefully that should get you everything you need. But anyway, that's kind of all the material that we've covered going up to the Unit 9 test, which will be tomorrow. So definitely prepare yourself for that.